Hello everyone. In the last section of this nuclear physics chapter, so in the two previous classes we were discussing about two different nuclear radiation detectors. So in that we have discussed the Geiger-Müller counter and the scintillation counter. In today's session we will discuss about the particle accelerators. So in that particle accelerator, we will study about one of the accelerator called as the linear accelerator, which is commonly called as LINAC. So in today's session, we will discuss about the construction and working of this linear accelerator or LINAC. The linear accelerator, which is oftenly called as the LINAC, is a type of particle accelerator that accelerates the charged particles or ions to a high speed by subjecting them to a series of oscillating electric potentials along a linear beam line. So this linear accelerator or LINAC is a type of particle accelerator which can accelerate variety of particles starting from electron, proton, even up to heavy ions, that is even lead or uranium-235. These heavy ions can also be accelerated by this linear accelerator. So how this linear accelerator accelerates those subatomic particles as well as the heavy ions? So it accelerates them by subjecting a series of oscillating electric potentials. Means by applying higher voltage, it increases the velocity of the subatomic particles as well as the heavy ions. So if the velocity is increased, as the velocity is directly proportional to energy, so we can increase the energy so that one can extract high energetic beam from this linear accelerator for the various kinds of experiments. So if you look at the block diagram of this linear accelerator, at first it consists of the ion sources. So ion sources means it is an injector which injects the variety of ion beams. That may be electron, that may be proton, or any kind of heavy ions starting from alpha particle to even up to lead-208 or even uranium-235. So such ions will be injected in that ion source. So for that injection also we require a high voltage source. So initially it has ion source. From that ion source we can extract or we can inject the required subatomic particles or heavy ions which are to be accelerated in this accelerator. So after that ion source we have a hollow pipe of vacuum chamber which consists of drift tubes, cylindrical tubes which are separated by certain distance. So in that gap only, by applying higher voltage, one can accelerate or one can increase the velocity of the ion beams which are injected from the ion source. So for that purpose also we require the high voltage potential. Then after that the radio frequency source is also applied to change the polarity of the drift tubes so that electrons from one drift tube which is negatively charged can be moved towards the another drift tube which is positively charged. So in simple, this linear accelerator or LINAC consists of the ion source and a hollow pipe of vacuum chamber which consists of a cylindrical tubes. So this is the block diagram of this linear accelerator. Then if you look at the construction of this LINAC or linear accelerator which we have discussed now, the first component is the particle source or the ion source which is also called as the injector. The design of this ion source depends on the particle that is being moved. Means depending upon our experimental requirements, we can use the different types of ion sources. Suppose if we want to accelerate or if we want to generate electrons, then such electrons are generated by either by a cold cathode or by a hot cathode or by a photocathode or by radio frequency ion sources. So in that ion sources, the electrons can be generated either by cold cathode or by a hot cathode or by a photocathode, means which we have discussed in the case of scintillation counter. When certain radiations incidents on the photocathode of the photomultiplier tube, it ejects the electrons based on that photoelectric effect. So similar to that, in the ion source, the electrons can be generated by using a cold cathode or by a hot cathode or by a photocathode or a radio frequency ion sources. So this is for generation of electrons in the ion sources. Then suppose if we want to generate the protons, then protons are generated in an ion source which can have many different designs. So depending upon our experimental requirements, we can generate variety of ion beams. Apart from this electron as well as proton, suppose if we want to generate or if we want to accelerate the heavier particles or heavy ions, such as alpha, starting from alpha particle even up to lead or uranium-235. For acceleration of such heavy particles, a specialized ion sources is needed. So depending upon our experimental requirements, we can use the different types of ion sources. So the basic idea behind this ion source or the principle of this ion source is, depending upon our experimental requirement, it can generate the ions or particles, subatomic particles such as electrons or protons or heavy ions. So the generated subatomic particles or the heavy ions will be accelerated in that hollow pipe of vacuum chamber which consists of drift tubes. So the ions will be accelerated in those gaps between the drift tubes. So this is the first component, that is particle source or the ion source which generates the different types of ions in this linear accelerator. So that is the first thing. So in order to inject those ion source into the accelerating column, we require certain high voltage source. That high voltage source for the initial injection of the particles means the particles or heavy ions generated in this ion source or the particle source will be injected into the accelerating column by applying certain high voltage source. So the first one is ion source which can generate variety of ions or heavy particles or beams, and such ions or beams, heavy particles, will be injected into the accelerating column with the help of high voltage source. So that is the second component of this linear accelerator. The first one is ion source which can generate different types of ions, and those ions will be injected into the accelerating column with the help of the high voltage source. So these are the two main components of this LINAC, and after that a hollow pipe of vacuum chamber which can be called as the accelerating column. Means in this hollow pipe vacuum chamber, the ions or heavy particles injected from the ion sources will be accelerated. So this is called as the accelerating column, that is a hollow pipe vacuum chamber. So the length of this vacuum chamber or hollow pipe varies depending upon the applications or depending upon the experimental requirements. The length of this hollow pipe will vary with the application. For example, if this linear accelerator is used for the production of X-rays for inspection or therapy, means suppose using this linear accelerator, we are extracting X-rays for some inspection purpose as well as for some treatment, that is for therapy. Then the length of this hollow pipe ranges in between 0.5 to 1.5 meters. So depending upon the applications, the length of this hollow pipe changes. So for the production of X-rays, which can be used for inspection as well as for treatment, the length of this hollow pipe ranges in between 0. If the device is to be an injector for synchrotron, synchrotron is an electromagnetic radiation which is of the type of cyclic accelerator. For that purpose, if we want to inject the electrons into that synchrotron storage ring, or the electrons from the ion source which can be injected into this synchrotron radiation source. So for that purpose, the length of this hollow pipe vacuum chamber is about 10 meters. So in order to generate the synchrotron radiation, which is also a type of electromagnetic radiation which can be used for variety of applications such as the protein crystallography, and then X-ray fluorescence studies and all other things, that synchrotron radiation can be used. For the generation of that synchrotron radiation, initially we have to inject the electron beam which can be extracted from that linear accelerator. So for that purpose, the length of this hollow pipe vacuum chamber should be about 10 meters long. So this is the second type. If this linear accelerator is used as the primary accelerator for nuclear particle investigations, then in such cases the length of this accelerating column should be several thousand meters long. Means the length is of the order of 1000 meters. So depending upon the variety of applications, the length of this accelerating column changes. So for the production of X-rays which can be used for inspection or therapy, means for treatment, it is in the range of 0.5 to 1.5 meters. Then for the injection of the electron beam from this LINAC into the synchrotron radiation source, then in that case the length of this accelerating column is about 10 meters. Then suppose if we want to use this linear accelerator as the primary accelerator for different types of nuclear particle investigations or different nuclear reaction investigations, in that cases the length of this hollow pipe or the length of this linear accelerator is about several thousand meters long. So depending upon different types of experiments, this length varies. So within this chamber, that is hollow pipe vacuum chamber, the electrically isolated cylindrical electrodes are placed, which can be called as the drift tubes, whose length varies with the distance along the pipe. So these cylindrical electrodes length varies with the distance along the pipe. The length of each electrode is determined by the frequency and the power of the driving power source and the nature of the particle to be accelerated. So the length of each electrode or each cylindrical electrode can be determined by the frequency, the power of the driving source and the nature of the particle which we are accelerated. As we have discussed in the previous case, for X-rays it is about 0.5 to 1.5. For the injection of electron beam into synchrotron, it is about 10 meters. Then for the use of primary accelerator in the case of nuclear particle investigations, its the length is in the order of several thousand meters. So depending upon that, the length of the cylindrical electrodes also varies. So and the nature of the particle to be accelerated with shorter segments near the source and the longer segments near the target. Means the length of the cylindrical electrodes is small near the ion source and the length of the cylindrical electrode is long near the target. Means as we keep on moving from the ion source, the length of each cylindrical electrode will be increased. So this is the third component of this LINAC, that is hollow pipe vacuum chamber, which consists of cylindrical electrodes, and this is called as the accelerating column of this linear accelerator. Then the mass of the particle which we are accelerating in this hollow pipe or the accelerating column has a large effect on the length of these cylindrical electrodes. So the mass of the particle plays an important role in the length of these cylindrical electrodes which we have placed in the hollow pipe vacuum chamber, which is generally called as the accelerating column. For example, an electron is accelerating, means in this accelerating column we are accelerating the electron. Suppose if we are accelerating the electron and its mass is lighter than the proton. An electron is considerably lighter than a proton, which is clearly evident because the mass of the proton is of the order of 1.67 into 10 raised to minus 27 kg, whereas the mass of the electron is about 9.1 into 10 raised to minus 31 kg. So the protons are 10 raised to 4 times heavier than the electron. That's why an electron is considerably lighter than a proton. So generally require a much smaller section of cylindrical electrodes as it accelerates very quickly. So the mass is smaller or lighter than the proton. Therefore, this electron acceleration requires a much smaller cylindrical electrodes for this acceleration. Likewise, because its mass is so small, that is mass of electron is so small, electrons have much less kinetic energy than protons at the same speed, because the kinetic energy is given by the expression half mv square. Even the electrons and protons are at the same speed, the kinetic energy of protons is greater than the electrons, or the kinetic energy of electrons is smaller than the proton at the same speed because they are lighter than the protons, that is about 10 raised to 4 times. So because of the possibility of electron emission from highly charged surfaces, the voltages used in the accelerator have an upper limit. So this can't be as simple as just increasing voltage to match the increased mass. Means by increasing the voltage we cannot match the mass of that electron, which is equivalent to the mass of the proton. So in general, for the acceleration of the electrons in this LINAC, we require a smaller section or small series of those cylindrical electrodes in comparison with the acceleration of the protons. So in this, one or more sources of radio frequency energy used to energize the cylindrical electrodes. So in this accelerating column only, or in this hollow pipe vacuum chamber, one or more sources of radio frequency energy is used. It is used to energize the cylindrical electrodes. Means these radio frequency sources will be used to increase the energy of the cylindrical electrodes. A very high power accelerator will use one source for each electrode. Means a high power accelerator can use one radio frequency energy source for each electrode. Means if the number of electrodes present in that high power accelerator is equal to 10, then we should use 10 different radio frequency energy sources to energize or to increase the energy of those cylindrical electrodes. The sources, means the radio frequency energy sources, must operate at precise power, that is at definite power, frequency and phase appropriate to the particle type to be accelerated to obtain the maximum power. So these radio frequency energy sources must be operated at a precise power at a definite frequency and the phase which is appropriate to the particle type which we are accelerating in this accelerating column to get or to obtain the maximum device power. So this is the third component of this LINAC. The first one is ion source, which can generate the ions, different types of ions, and the second component is high voltage source. Using that high voltage source we can inject the ions into the accelerating column. Then the accelerating column, that is a hollow pipe vacuum chamber which consists of the cylindrical electrodes. Using that cylindrical electrodes with the help of the radio frequency source as well as the high potential difference between or the gap between two consecutive cylindrical electrodes, we can accelerate the particle in that accelerating column. So that is the third one. And the fourth one is an appropriate target. So at the end of that accelerating column we have certain targets. So again, depending upon the experimental requirements, the electrons which are accelerated or the different ions which are accelerated in that accelerating column will be used or will be focused onto the different targets to generate different types of radiations. Suppose if we are accelerating the electrons in the accelerating column, then those electrons can be used for the generation of X-rays. So if electrons are accelerated to produce X-rays, then those electrons are made to incident on certain target. For example, a tungsten target which is water cooled. So water cooled tungsten target is used to generate the X-rays from the electrons. So when the electrons incident on that tungsten target, so because of this interaction between that electron and the electrons of that tungsten target, there will be ejection of certain X-rays which we can call it as X-ray fluorescence phenomenon. So those X-rays can be used for different types of experiments. So if electrons are accelerated to produce X-rays, then water cooled tungsten target is used. Various target materials are used when protons or other nuclei are accelerated depending upon the specific investigation. Means depending upon our experimental requirement, we can use different types of targets. So one example here is electrons are used or accelerated to generate X-rays. So for that purpose we can use a water cooled tungsten target. For particle to particle collision investigations, the beam may be directed to a pair of storage rings. So these storage rings means in the case of synchrotron radiation, which we have discussed earlier in this case. So that is a storage ring. So for particle to particle collision investigation means one particle collides with another particle. So for such type of investigations, this beam from the LINAC will be directed to a pair of storage rings with the particle kept within that ring by the help of magnetic fields. So the beams may then be extracted from the storage ring to create head-on particle collisions. So for particle to particle collision, these beams from the LINAC will be directed into the storage rings. So these particles will be kept within that ring with the help of magnetic field, and after that the beams inside that storage ring can be extracted from that to create the particle collision. So additional magnetic or electrostatic lens elements may be included to ensure that the beam remains in the center of the pipe and its electrodes in that storage ring. So these are different types of targets, or we can call them as the different applications of this linear accelerator. So in general, this linear accelerator consists of ion source which can generate different types of ions. those ions will be injected into accelerating column with the help of high voltage source. So in that accelerating column, which is a hollow pipe vacuum chamber, the ions will be accelerated with the help of cylindrical electrodes. Then, depending upon our experimental requirements, we can use different targets to generate X-rays using electrons which are accelerated in the LINAC. We can make use of the tungsten target. Then for protons as well as for other nuclei which are accelerated in the linear accelerator, we can make use different types of targets depending upon our experimental requirements. In the same way, in order to study the collision between two particles, these beams which are extracted from the linear accelerator will be directed towards a pair of storage rings. So in that storage ring, these particles will be kept with the help of magnetic field, and after that these beams will be extracted from the storage rings to create head-on particle collision. So in general, depending upon our experimental requirements, we can make use of different types of targets. So this is about the construction of this linear accelerator or the LINAC. Then how this linear accelerator works. So ion source gives bunch of electrons which are then accelerated towards the first drift tube. So suppose, for example, we are considering the ion source generate the electrons. Okay, so those electrons will be accelerated towards the first drift tube, means first cylindrical electrode. This is because the first drift tube is positive, means the charge of that first drift tube is positive, whereas the charge of that electrons is negative. So ion source gives bunch of electrons which are then accelerated towards the first drift tube. This is because of their negative potential, that is negative potential of the electrons, and drift tube's positive potential, means the electrons are negative and the first drift tube is having positive potential. When electrons comes inside that first drift tube, in that moment the radio frequency source shifts the polarity of that first drift tube. So because of this radio frequency source, the polarity of that first drift tube is changing. So first drift tube then becomes negatively charged and the second tube is positively charged. So because of this opposite charge, electrons come outside of tube because of its inertia, and in that moment they are pushed into the second drift tube from the first drift tube. So in between there is a gap, and in that gap, by applying certain potential, the velocity of the electrons will be increased. So as the velocity increase means the energy is also increased. So within the gap of two consecutive drift tubes, the ions will be accelerated, means the velocity is increased so that the energy is also increased. As electrons are accelerating, their velocity becomes bigger and they travel longer distance in the same time. So that is the reason why drift tubes must be longer as electrons comes closer to the target because of their greater velocity. So in between two consecutive drift tubes, the electrons will be accelerated, means the velocity is increased so that the energy is also increased. So as the electron travels from the ion source towards the target, the length of the drift tube increases because of the greater velocity. So because of their greater velocity, the energy is also increased. So such high energetic, high velocity electron beam can be extracted from this linear accelerator for variety of practical applications. So as the particle bunch passes through the tube, it is unaffected. So those particles will be unaffected, while the frequency of the driving signal and the spacing of the gaps between electrodes are designed so that the maximum voltage differential appears as the particle crosses the gap. So this maximum voltage difference or potential difference accelerates the particle. So because of that acceleration, this maximum voltage difference imparts, means provides energy to it in the form of increased velocity. So in brief or in summary, we can summarize this construction and working of this linear accelerator as, so this linear accelerator consists of ion source which generates the ions. Then such ions will be injected into accelerating column with the help of a high voltage source. Then in that accelerating column, when those ions will be injected from ion source into that accelerating column, which is a hollow pipe vacuum chamber which consists of cylindrical electrodes. So towards the end of that ion source, the length of those cylindrical electrodes is small, and towards the target the length of those cylindrical electrodes is the large. So this is because of the greater velocity of the electrons which are accelerated in the gap of two consecutive cylindrical electrodes. So how these electrons will be accelerated in the gap of two consecutive electrodes? This is by applying certain maximum voltage difference or potential difference. So by applying that potential difference, one can increase the velocity. So if there is an increase in velocity, means there must be increase in energy, so that we can say that the ion beams, to be specific, the electrons are accelerated. So as the electrons are passing from one cylindrical electrode to another cylindrical electrode, there will be increase in velocity as well as the energy. So this is the construction and working of this linear accelerator. So this linear accelerator can be used for variety of applications. Means advantages of this linear accelerator are, it can be used for production of X-rays, which can be used for the radiotherapy treatment, means in the field of medical, means medicine. We can make use of the X-rays which are generated from this linear accelerator, can be used for radiotherapy treatment. Then these linear accelerators can be used for generation of synchrotron radiation, and it can be used for it can be used as the primary accelerator for the nuclear reaction studies. So these are some of the applications of this linear accelerator. Then the disadvantages, or the main disadvantage of this linear accelerator is, suppose if we want to use this linear accelerator as the primary accelerator for the nuclear reaction studies or nuclear particle investigation, then the length of this hollow pipe is of the order of few thousands of meters, means several thousand meters long. So for the construction of such long linear accelerator means it is too expensive, and it acquires maximum space, and these are some of the disadvantages of this linear accelerator. Means the several thousand meters long linear accelerators, construction of such long linear accelerators are bit expensive, and it acquires a larger space. So these are the advantages and disadvantages of this linear accelerator. So in today's session we have discussed about this construction and working of linear accelerator, which is one of the particle accelerator which can accelerate variety of particles. And after that we have also discussed in brief about the advantages and disadvantages of this linear accelerator. Some of the advantages are, it can be used for generation of X-ray, It can be used for generation of synchrotron radiation, and it can be used as the primary accelerator in the case of nuclear reaction studies. Disadvantages are it is bit expensive, as well as it takes a large space to construct several thousand meters long linear accelerators which can be used for nuclear reaction studies. So this is all about the construction, working, advantages and disadvantages of this linear accelerator or the LINAC. So in the next session we will have the discussion on one more particle accelerator, that is cyclotron, which is the example of cyclic accelerator. So we will discuss that cyclotron accelerator in the next session. Thank you.